Welcome everyone. Today I'm talking with Kushanav Bhuyan and Kamal Rana about their recent study in Nature Communications, where they are studying landslide shapes, morphologies, and topology, and use this information to talk about landslide movement types. And this again is very important data that can be used in, for example, landslide predictive modeling. And yeah, I'm very happy to have those two with us today. In this study, you are looking into the topology of landslides, and based on the topology, you are trying to figure out how the landslides moved. So I think my first question would be, why is it important to understand how a landslide moves, and what different movement types are we talking about?
I think it sort of boils down to the very nature of why we're sort of in this business of looking at the hazards, or let's say the disasters which eventually come up in terms of the impacts that you might have from climate change. So in that case, I'm talking about heavy precipitation changes in the climatological settings, and also looking at, for example, seismic activities, because this information sort of related to the failure types are also linked to the triggers themselves, but also including a lot of the information that comes into the topography of the landscape as well. So now the reason why I'm saying this is because eventually you want to be able to design models, particularly predictive models, that can allow us to gauge where these landslides or quote unquote landslides would happen, because landslides as a term is quite an umbrella term. And if anyone reads the paper, that's what they'll figure out, because when we say landslides, we're also talking about very distinct types of failure movements. And usually what happens, particularly with data-driven models, is that when you build such predictive models, you sort of combine all of these different mass movements or landslides, as you might say, and then you sort of make this predictive model. But in reality, each of these movements have different mechanisms, have different kinematics. They basically behave very differently, particularly if you look at some, for example, let's say rock falls. They are sort of hanging at the cliff and they just fall down. And you might imagine that this is completely different than if you look at traditional sliding mechanisms. So that's one of the reasons why, because it really allows us to have, let's say, tailored specific predictive models, so that if you have a data set which are particularly rockfall, then you might have more nuanced, more accurate rockfall predictive models, rather than having something which is a bit homogeneously defined.
Thank you. And sticking with the topology, can you briefly explain how you define topology? What parameters are you looking at? And also, in particular, in your study, how did you measure topology? Did you go into the field, or did you use remote sensing data, or what was your approach towards this?
So in landslides, all the data that we have is from polygon. And this polygons data we got from either satellites or drones. So these polygons are actually 2D. So what we did in our work, as Kushanav said, that this failure types information is embedded in the landslide 3D shape, not the 2D. So we use the elevation data that is available. So we convert these 2D polygons to 3D shape. Now, when we convert these polygons into 3D shape, we also capture the 3D information of landslide, like how their slope, variation, how their curvature looks. We got all this information. And in 3D shape, we can also, it captures topology. So you can assume topology is like geometry, but it's not sensitive to changes. For example, you have a 2D polygon, even you bend it a bit, it will not change. So we come up with this idea that these ideas are less sensitive to noise. So based on this information, we can kind of clusters same failure types landslide into one group. And then we thought we can use this information topology from landslide, build a machine learning model, and classify them.
So now we have talked about the topology and the landslide movements that you were observing in general. And then also in your study, you are looking at events across a variety of geographic and climatic regions. First of all, why do we need to look at all those various landslide events in different geographic regions? And second, are there any specific landslide or movement types that are typical for certain geographic regions?
I think in terms of when we look at the geographical diversity, I think this answer is sort of two-pronged. First is from the model's perspective, in terms of looking at the general, let's say, adaptability of any sort of model that you have. Because if you build a model but it cannot be used elsewhere, then it's sort of, let's say, region specific. And that's also sort of what we figured out, because initially the plan of any, when we were starting this research out, was to look at the literature and try to find what was missing really. And some of the biggest things that we found out was that in order to have something which is adaptable, you need high dimensional, particularly in this case, you need some information which is very deeply rooted in the topography. But again, topographies change dramatically over different landscapes, and by proxy, and I'm talking about different geomorphological settings. So that's one of the reasons why we wanted to go to different geographical locations, which is the first prong. The second prong is that we also have to realize that even failure movements, and let's say, let me take a very simple example of a rockfall again, let's say. So if you take a rockfall in region A, and if you take another one which is like thousands of miles away or kilometers away, they are still rockfalls, but they could behave quite differently as well, particularly depending on where they initiate. If it initiates quite close to the ridge of the mountain, versus if it initiates at the mid-range of the topography, or at the close to the valley bottom, let's say, their kinetic energies are going to be quite, let's say, dramatically, it's going to be dramatically different. So you have these also nuances, not just related to the model, but also the very behavior of even similar failure mechanisms or movements, which can be very different across different topographical or geomorphological settings. Yeah. And could you please repeat your second question? I think I sort of misread it.
I think the second question was really just about, are there any landslide types or movement types that are very typical for certain climatic regions?
It has to do not just with the climatic, let's say, settings of the regions, but also because it's a sort of a game of chain events, because it's a combination of your climates, and that probably we're talking about, let's say, the conditions of the conditions that the climate also sets into the not the geology, but the lithology as well. So if we look into that, you can find very different conditions that are present in the let's say, geomorphology, which are very differently triggered by even changes in the climatological variables. So you could have different responses as well. A good example of this could be, let's say, the 2008 Wenchuan earthquake. So after the 2008 Wenchuan earthquake happened, you had a lot of this co-seismic landslides. And what happened was that a lot of these materials were sort of suspended. When they failed, they sort of got suspended here at the bottom, but then it didn't move out of there. So it was still, let's say, relatively safer or relatively okay. But after 2 or 3 years, there were heavy post-monsoonal, let's say, like heavy monsoonal rainfall. And it sort of remobilized all those material which came down. And that really created a lot of problem moving forward as well, apart from what the earthquake itself created as issues back in 2008. So you have this sort of chain events, like seismic chain events, coupled with climatic factors, which, despite the geology or lithology being the same, or the topography remaining the same, the climates of that region really played a role in, let's say, shaping the landscape in terms of how these materials, suspended materials from before, got mobilized later on.
I think then from really a natural hazard perspective and hazard mitigation perspective, one of the most important questions here is how do the results you presented in your study, how can they be implemented into hazard mitigation efforts? You already talked about modeling. Is this the way forward to implement this, or how do you think about helping landslide prediction?
So the landslides, like you can understand that landslide with same failure types has similar properties. So to make a better landslide predictive models or risk models, you want to cluster them. So for example, slide is better to have like a specific predictive models that only focus on slide landslides. So before our work, there was no such method exist. So what people do, they mix all the data together and predict landslides or regions that are prone to landslides. So after our work, I think landslide experts or practitioners, they can first cluster the entire landslides database into different groups based on how they fail, and then they can use that data set for predictive models. I think Kushnav can go more in details now.
No, I think what Kamal said was basically in the line with which I was going to explain as well. But I think I'll just add a couple of more points, but very short points, which is that when you look at a typical predictive model, let's say outputs of what a model is going to give you, like, okay, you have this location and it's going to say, okay, it has a probability of 90% of, let's say, a failure of a type, or let's say a failure of landslides. But again, like how Kamal said, if you combine them, you don't know which type or which sort of which particular movement is going to propagate or it's going to happen. So, and also for different types of movements, you have different mitigation measures. For example, let's take a very simple example, Gabion walls. Right? So for certain types of landslides, let's say rock falls, you would install those kind of engineering measures, but for others, you might have some different type of engineering measures to mitigate those hazards. So if you have this information, which are very type specific, uh, or let's say movement specific, you can address the mitigation through those kind of measures, be it engineering or be it ecological, be it nature-based solutions as well. So it goes hand in hand, actually. So that's what we were trying to also put forward in the paper as well.
I guess my final question would be, is this project finished, or what are the next steps you want to look into or you want to address in this research area?
Probably Kamal can add more a bit after I finish. I think we have sort of, let's say, when we sort of finalized our results, even before writing the paper, we felt like we sort of opened a Pandora's box, because there's so many different avenues that we can actually go into. I mean, one of the things that we talked in the paper was also looking at Martian landslides, for that matter. So that's one avenue. Another avenue is probably we can also look at submarine landslides, because even they have different types of failure movements, but their behavior is very different because they're underwater, under aquatic conditions. Another thing that we are currently working on is also expanding into even more study areas that so we can find sort of really move forward to what we were talking a couple of minutes ago, particularly those predictive models. So one of these aspects that we're looking at now is we have an inventory, a database, we classify that, and then we try to, let's say, compound or build on those information to have more, let's say, accurate predictive models. That's one direction that we're going as. But I do foresee a lot of, let's say, other applications that could be possible. But again, that's why we need some continued collaboration also with the other geoscientific community who actually deal with let's say shapes, for that matter, or any sort of a morphological unit that can be quantified as a shape, and then that's where you would try to find a sort of imprint or let's say a footprint of that morphological dynamic that you want to extract from the topography.
In our work, we develop a method just based on the landslide 3D shape. And based on 3D shape, we tell that there is some differences between different failure types, and we can use topology to classify them. So I think our method can be used in different landslide research. So one of the application is trigger classifications. You can use earthquake landslide dataset and rainfall landslide dataset and use them to classify. Also, it can be used to study landslides in general, because in our work we saw that landslides can be caused by so many different factors, and just based on the say we can extract most of those information, and using this information we can study landslides.
Well, thanks again for your time. I think that's all the questions I had in mind. So I think this was very insightful. Thanks.
Thanks so much for your time as well.
Thanks, Sebastian.